A very good morning to all of the participants, esteemed speakers, our honorable principal sir, the students, research scholars, and others. Welcome to the second day of our national webinar named Current Status and Future Scope for Nanomaterials and Nanotechnology. The first day session was a very big successful one. We came to know about different aspects of nanomaterials and nanotechnology from our four esteemed speakers. Today's session is also likely to be enriched with the five esteemed lectures. With the permission from our honorable principal sir, I would like to start our today's session. Our first speaker is Dr. Navnita, who is an assistant professor of physics, Bihar University, Muzaffarpur. Her title of the talk is Nanomaterials, Broad Spectrum for Device Application. Dr. Navnita research area of interests are structural studies of metal oxide nanoparticles, electrical transport mechanism in metal oxide nanoparticles and its properties for transparent conducting oxides and optoelectronics, and many others. She has been the principal investigator of a project entitled Surface Engineering and Interface Study of CZTS Absorber Layer for Solar Cell Application, funded by ACRB DSP, New Delhi, Government of India. So now I would like to request our first speaker, Dr. Navnita, to start her lecture. Thank you, ma'am. Ma'am, please unmute yourself. Okay, you are not audible, ma'am.
Hello.
Yes, now you are audible.
Can you hear me?
Yes, ma'am. We can hear you.
Good morning to everyone, especially from Mahila Kala Bhawan College that in this pandemic situation they have tried at their best to organize this webinar. So today my topic of talk is I am sharing my screen.
Yes, ma'am.
Is it visible?
Yes, ma'am, it's visible.
Okay. So today I'm going to provide a little bit application spectra by using the nanomaterials. Why we have to use the nanomaterials? It's a broad spectrum for device application. When uh, when we move towards bulk to nano, there are lots of properties of the material has been changing, and by using that property, we can further use that materials or that particles for further device application, which is right now in a very efficient way we have to use it. Such if we can think that nanomaterials as a technology or as a device application, there are lots of things which we can see from this PPT that we can manage for the air pollution, for water treatment and filtration. Water treatment and filtration, TCO, that is a transparent conducting oxide, battery, in cosmetics, in medical application, in drug delivery system, robotics and space technology, artificial intelligence, and food processing. And the most important factor is towards energy application and energy storage. I already studied that lots of speaker is in this talk, and yesterday and today's webinar there are lots of regarding the drug delivery, that energy harvesting, that information technology, and the medical treatment. This is the era of the nanotechnology. But when we move towards the nanotechnology, the first thing is to choose the size and shape of the particles, which must be at the nano level. Why we have to think about the nanomaterials, which is a fascinating world of application. The nano range is always in between 1 to 100 nanometer. The range is a quantum region. The nanomaterials exhibits a quantum effects that makes them highly suitable for the electronics, optoelectronic devices, in semiconductor devices, in a quantum technology also. There are many different classes of nanomaterials, which includes thin films, nanoparticles, nanorods, nano in the nanoflowers, and we have this different shape and size provides a various dimension of research for the application purpose. The physical and chemical properties of nanomaterials are closely related to the size, shape, and surface, which is also called the 3S structure or 3S concept, as well as from the volume ratio. It having the high percentage of surface atoms as compared to bulks, due to which various properties has affected, such as melting point, boiling point, band gap, reactivity, mechanical, electrical, magnetic, electronic strength, and as well as optical properties. When we say about the nanoparticles, there are lots of materials which is already exhibits inside the nature, which is called the natural nanoparticles, such as we can see on the flower petals. There are small structures on a lotus leaf, etc. Some are the man-made nanomaterials, which is incidental. When we use when we see that the train chemicals which is exposed from the different industry, and some nanomaterials are engineered. That is a nanomaterial which having a different morphology, such as a nanocubes, nanorods, nanoflower, nanoribbons, etc. And now these scale materials can be widely used for a different application. If we think about energy harvesting, then by using this type some materials, we can go for the energy harvesting, and we can harvest the energy such as a photocatalysis, photovoltaic, supercapacitor, hydrogen generation, and a lithium ion batteries. Now move towards how we synthesize that nanomaterials, how we have to prepare it for our application purpose. First, we have two methods mainly, that is top down or bottom up approach. If we move from the top down approach, then we have to take the bulk materials, and we use that bulk materials by cutting or by doing any mechanical or chemical means and going towards the smallest particle. And when we move towards the bottom up approach, then we take the atomic and molecular level, and we move towards the nanoparticle range. In case of bottom up approach, there are lots of methods, which is atomic molecular condensation, vapor deposition, spray pyrolysis, bioreduction, solvothermal, and hydrothermal. And when we move towards the top down, then sputtering, chemical etching, mechanical ball milling, explosion process, thermal laser ablation, etc. is required. So for the top down and bottom up approach is also very much dependent on the 3S, that is a uh, surface size and sensitivity. So for if we move towards the surface properties of that material, then surface shape of material, size of the material is plays a very much important role. Such as we knew about the carbon nanotube, some graphene, polymers, metallic nanoparticles, dendrite meter, hydrogels. So it's up to you on which application you want that, which type of shape and size of that nanoparticles. If we move towards the nanotechnology and energy generation, then because I am mostly highlighting about the energy because right now we all are suffering from the energy crisis and we have to pay the electricity bill and all. So if we move once towards the different types of energy harvesting by any mean, by using the solar sunlight or by water, etc., then we can be dependent on energy but not on the by other renewable resources. We can use that resources which is easily available in on the earth and from the sunlight also. So energy conservation by using the fuel cell, solar cell, thermoelectric, piezoelectric properties, supercapacitor, energy transmission by the insulating materials, that is also a superconductivity, nano lubricants, smart window, nano refrigerators, and these are also the energy saving way for us. And this technology can be further used for the environmental science, information technology, biotechnology and medical application, automatic automobile industry, textile industry, etc., and as well as agriculture in agriculture science energy. Here we can see how the nanotechnology can boom our lifestyle. Earlier, this type of computer we used, but now we move towards a very thin and slick. Now we use this type of phone, very small and thick. So it's only due to the boom of the nanotechnology. Now when we prepare the nanoparticles, the first duty to characterize its characterization techniques. If we go for the characterization techniques, then it's a must essential part that yes, the particle which we made via any top down approach or via bottom up method, it is made up of the nano size, nano range or not. So for several techniques has been used to characterize the size, crystal structure, elemental composition, and a variety of other physical properties of the nanoparticles. In several cases, there are physical properties which can be evaluated by more than one technique for the better accuracy and optimization for the device application. The different strengths and limitations of each techniques complicate the choice of the most suitable method, while often a combinational approach of characterization techniques is required for scientists and researchers. In addition to that, the significance of nanoparticles in basic research and application is constantly increasing. And after their synthesis and further processing, like as annealing, etc., for further characterization is required. So different characterization are classified according to the concept and group of the techniques used. The information can be provided on the nanomaterial which are destined for a different application as a device fabrication. There are lots of energy entity characterization which has been used for a different application and it shows the different properties such as size distribution, TLS, SX, NTA, FMR, supermagnetic relaxivity, SEM, etc. The surface charge, zeta potential, EPM, single particle properties, HRTEM and liquid TEM, 3D visualization, 3D tomography, AFM, SEM, etc. For structural defects, we have to use uh, the HRTEM, EBSD, etc. For optical properties, UV visible, FESC, FE, NIR, UV visible NIR, photoluminescence, EELS, STEM. Magnetic properties, squid, SEM, Mosware, MFM, and magnetic susceptibility characterization techniques. If we move towards the optical properties, first we take the structural characterization, then we move towards the optical, that yes, that material, if we are going to make the optoelectronic device, then we must know about the optical properties of that nanomaterial which we have to made. So for that, we have to go for the optical properties and optical characterization of that material. The electrical characterization, which is the mobility, carrier concentration, contact resistance, etc. And if we move towards the magnetic properties, which we have to take the magnetic force meter, MFM, superconducting quantum interface devices, that is a SQUID also. But now, for telling about all these, that when we made the nanoparticles and after that nanoparticles we made the device application. After further characterization, the device which we have to use is much more efficient. But in this technological era, and we are doing it all the things without thinking about the future. Can we think when we made the solar panels? It's a huge, and it takes a lots of space. But when we can we think that after 25 years or 40 years or 50 years, when we will where we will dump that solar panels, or if we will dump in the earth, how it affects to our natural system? Yes, it's a big question. Right now, we are just thinking about, yes, nanotechnology is good. We can use that nanotechnology and we can use that nanomaterials. But it's a future is also we have to think, because when we made that all types and we can manipulate all types of properties, it's also in future it may be possible that it can be create a havoc for us. Sometime in 1986, one person has told about the grey goo, that is the end of the world scenario involving molecular technology in which out of control self replicating robots consume all biomasses on the earth while building more of themselves, a scenario that has been called ecophagy. It means that nanomaterials or nanoparticles have changed itself, and it can be made like a gigantic robot, and it can consume just such as just you think just now we are suffering from the coronavirus. Why we are suffering? Because that virus had changed and manipulated itself according to the atmosphere or times, so we are unable to overcome it. So it may be possible after 100 years or after 200 years, it may be that nanomaterials and nanotechnology can become the grey goo. This term emphasized the difference between superiority in terms of human values and superiority in terms of the competitive success. Right now, we are in the competitive success. I think from the America or from the China, from any other countries which is developed or underdeveloped. So we are trying to make ourselves superior. Yes, it's true, because the real strength is only resides in the power. But during this power, we have to keep our moral and mental values in terms of making that nanotechnology or nanoverse. Because if we can start the bio weapons by using that nano materials properties, then it can be disaster for the world. The world's within a few days or few hours, the whole world can be destroyed. The artificial replicator must not be capable of operating in a natural, uncontrolled environment. They must have an absolute dependence on an artificial fuel source or artificial components not found in the nature, and they must use encryption codes to prevent unintended alterations in their blueprints. Who knows that coronavirus is also a type of these type of things? If we are not to avoid major disaster, rules must set out to ensure safety. Researchers must be mentioned and manufacturers must be inspected during the preparation of the nanomaterials or nanotechnology. Now, this was a sad part, but we have to keep in that also in mind that yes, apart from a lots of benefits, it's also have some drawback, just like a normal thing which also have the pros and cons. But now we move, if we think about the future of the nanomaterials, yes, it have a tremendous application. The right now for future is ocean cleaning micro sponges, because we know that ocean system is totally dirty and filthy right now. So if we want to go for that, then we use the ocean cleaning micro sponges, super strong materials which is used for artificial intelligence, weather protection for your personal devices. When we move towards outside, our phone, our laptop is with us, and if it's raining, we are panic that yes, it will go inside, water will go inside and it will be not work. So we have to think over that how we can create or manage our phone for a hydrophobic, so that the water can't be affect us. Disease fighting nanoparticles for a drug delivery, making instant replicas, which can also useful for any DNA types of problems. The new material, which is right now silicene, zerminin, and stannine. Silicene is a recent little bit work has been done on zerminin. Some lots work is going on, but stannine, that is a fourth compound of a carbon, silicon, germanium, and tin. By stannine is a very recent, and right now there is a not a single work has been done on the stannine. Some properties is it's some properties is shows like it's a graphene, but it's a much more efficient property residing inside it, which is which is which having stannine is. So I think time is also going to be over. So nanomaterials are the is I am finally concluding my talk. Nanomaterials are the essence of molecular synthesis, manufacturing, and engineering. Nanoparticle-based technology cover different fields ranging from environmental
Excuse me, ma'am. Yeah,
remedies to
you can
energy
take time.
generation and most recent application. Key components in the development of new advanced technology, but for the nanoparticles, characterization is an essential. And nanotechnology has a lots of potential as a futuristic approach, but would be largely governed by simultaneous progress in the newer, faster, simpler, and more efficient characterization techniques for nanoparticles for formation of the nanotechnology and device application. The laws of nature leaves plenty of room for progress, and the pressure of world competition are even now pushing us forward for better or for worst. The greatest technological breakthrough in history is still to come. So we have to do it, we have to perform it to make the nanotechnology for our application purpose or for device fabrication. But keep that things in mind that superiority must be the human, not for the nanotechnology or for the nano worlds or for the nanomaterials. For this, I am going to end this my talk. This is acknowledgements work from ISC Bangalore, some from the DRDO, and some from IIT Delhi, and NRF facility which I have provided at the IIT Delhi. So thank you, and thanks a lot for
Thank
providing
you,
me this
ma'am.
opportunity for my talk. If any question, kindly ask.
Okay, thank you, ma'am, for such a nice representation about nanomaterials. You have a very well explained lecture on the broad spectrum of device application. We have also thrown some light towards the drawbacks of nanotechnology and the futures aspects, how we can solve the problems. So now I will request our participants to ask their questions. If any questions, please raise your hand. We will unmute you. Okay, no question from the participant side.
I think answer is waiting to question me. Sir,
Yes.
you may ask.
Okay.
Yes. Good morning, madam.
Very good
I
morning,
want
sir.
to know why people are not working in standing. Is there problem of
Yeah,
stability of the
no,
material?
no, it's not like that. Actually, this is a very recent concept. It's a little bit, you can say that a sister of a graphene or a sister of graphene, and very few people knew about right now. So some work has been started in IIT Delhi. I actually, before leaving there, I have started it, but after that, when I came here, it's got stuck. If we want, we
Madam,
can do it. It's a very recent and a decent material, such as a graphene, but little bit its a characterization is a little bit a tough part. Only its a characterization techniques is only in IIT Bangalore, in IIT Bombay. So that
okay.
is a little bit tough part. Otherwise, it's a very fine material.
Okay.
Actually, lots of people are doing work in MOS2 and this type of 2D material to totally shift the idea from graphene to these materials. So again, working in standing, is it advantageous or not? That is also a concern.
Sir, actually, MOS2 is a that type of material which you can use easily, and it is easily available. But the difference in MOS2 and graphene is a very much, because when we use the graphene, or sorry, stannine, then it's a sister of graphene. It's a durability. It's a very strong, very durable material because it's a sister of a graphene. Means this is comes under the family of the graphene. But when we move towards the MOS2, that it is a sulfate materials. So for molybdenum sulfide, we use a different application. But when we move towards the stannine, it provides the different application.
Okay, ma'am.
Okay, thank
Any
you
more
very much,
questions?
Dr. Navnita. Any more questions from the participant side? You can ask
Ask,
any questions
ask
related
any
to
questions,
device.
relevant or irrelevant. At least I can also learn from you people. Yeah, someone, Rahul Kumar, is raising his hand. Tell him
Okay, okay,
to
okay.
ask.
Okay, Mr. Rahul Kumar, please unmute yourself.
Yes, ma'am. It was a very nice talk. And
Thank you.
my question is, you told
Can
about
I
the.
see you? I am unable to
Sir,
see you.
please switch on
If
your video.
possible, switch on your video. But if you are not comfortable, then it's okay. You ask your question. No issue.
Okay, ma'am. My question is like you mentioned about the disposal of the waste that will be generated as a result of nanotechnology. So uh, it it might be possible that we may use the biodegradable kind of nanotechnology, like sustainable nanotechnology materials for such constructions like manufacturing of solar panels and all. It might be possible in future, I think. So what's your opinion about this?
Actually, see, when we think about that solar panels, if we think about specific solar panels, and I already mentioned that it's a huge, the material which we are using, it's a sometime it's a hazardous, indium gallium cyanide, CZTS, etc. But CZ in comparison to other materials, CZTS, that is a copper, zinc, tin, sulfur, is a very less toxic and earth abundant material. But if we move towards the solar panel, then if you know that if any biodegradable material we using for the solar energy harvesting, then is it possible that that microbes or that thing will be survive the sunlights? I think they don't.
Okay, ma'am.
So
Ma'am,
yeah,
ma'am, one more thing which came in my mind, because I am from biology background. So,
it's okay, you ask.
uh, ma'am, like chlorophyll, it is able to convert solar energy into chemical energy.
Yes,
Yeah, it converts solar energy into chemical energy, and that chemical energy is in the form of electronic flow. So it is electrical energy. So if by nanotechnology, if we are able to simulate this process in artificial mediums, so I think one kind of uh, uh, one advancement will be there, which will be also sustainable in nature by using the structures like chlorophyll if we can generate in the laboratory.
it may be possible that we can generate inside the laboratory, but uh, when we do in the laboratory, it's optimized condition. Whatever we
Yes.
are doing inside the laboratory, this is the optimized condition which we are providing it, that this type of things will happen. But when we move that optimized condition in open source, in outside from our home or from laboratory, is it efficient and is it works there? That is a big question. Because when one device
Yes.
we are making inside the lab, I also made the solar cell one, and when we I was doing it,
Yes.
it's giving 1.6% efficiency inside the lab with optimized condition and all. But when I did it outside the lab, it was useless, it was not working. So for a single device, you have to go for the 7 to 8 process, and then after it will come in the industry or in the society, so that we know that it's also having a pros and cons. And when we are making for the device and biological device or anything, yes, we can mimic the nature.
Yes, ma'am.
We also are trying to mimic the nature. We are also are about to mimicking that natural property, because I already mentioned that some materials which is in nano size or nanomaterials is already exhibiting inside the nature. But when we are trying to compile it or to shift in day-to-day life or in the laboratory, it's a very tough, and sometimes it's maybe hazardous also.
Yes, ma'am.
So
Okay, ma'am.
Yes,
Thank you. Thank you.
thank you, Dr.
I think
Namrita.
I am able to provide your queries answer.
Actually,
Hello.
there are plenty of rules at
Yes,
the
ma'am.
bottom, as Feynman said. There
Yes.
are more
More
options for
rooms,
research,
yes.
more
So it
rooms.
may be possible for after 100 or 500 years. It may be possible, but right now we can't say. I also told about the stenine also. We are trying because it having this group of materials, but how much it will be successful, we can't say without putting the hands on it.
I think collaborative research from physics, chemistry, and biological background will
Yeah,
solve the problems and
it
will
may
invent
be.
something new. Okay, thank you, ma'am. Once again,
Thanks,
now we'll
thanks.
move forward for our next plenary section. Our next speaker is Dr. Ayan Mukherjee. He is an assistant professor of physics from Patliputra University, Patna. His title of the talk is Future Nanomaterials Based Energy Storage System. Dr. Mukherjee has done his PhD from the University of Bardhaman, West Bengal, and he was attached to the Department of Instrumentation Science, Jadavpur University, as a researcher. The field of research is in the area of nanomaterials and thin films, especially for sensors and superconductor applications. Currently, he is working at Ramratan Singh College, which is a constituent college under Patliputra University, Patna. Dr. Mukherjee has published 19 international research articles, 2 book chapters in material science, and a book on popular science. He is attached as reviewer in different journals, selected as senior advisor in Akash Ganga Science Magazine's advisory board, and a life member of the Indian Association of Nanoscience and Nanotechnology. Thank you, Dr. Mukherjee, for being a part of this webinar. And now I would request you to start your lecture. Thank you.
Okay, thank you. Am I audible?
Yes, you are audible.
Okay. So first of all, I would like to thank Dr. Nolin Bilochan, patron of this webinar, and also principal of Mahila Shilpakala Bhawan College, and Mala Mukhopadhyay, convener of this webinar and HOD physics of that college. So first, I would like share my screen. So everything okay, Mala?
Yes, yes.
Yeah, see the okay. So welcome to all the participants also of this webinar. In this talk, I would like to discuss about future of energy storage system, and the total work is done within the concept of nanotechnology. So I am not giving or the concept actually is from yesterday lecture and today lecture. You have also gained some knowledge about nanotechnology and different processes, how nanomaterials are made. Dr. Navnita Kumari also shows you the application of nanotechnology with different aspect. Also the energy storage system, we can use nanotechnology energy storage system. I will elaborately discuss about that, how we use material to store energy. Now the outline of our discussion will be based on why storage system is essential. We know in general we use battery as storage system. What are the advantage and disadvantage of battery? A new system known as supercapacitor, that is modified version of capacitor, how it is compared to battery, how a good supercapacitor material can be characterized, or how we will know about for a material whether it is a good supercapacitor or not. Current research that is ongoing in India on this supercapacitor material, and facilities available within our neighborhood institute to do research in this area. So, first of all, we all are aware about that using the fossil fuel or traditional energy sources that are creating a severe harm in our atmosphere. So what we have to do? We have to use renewable energy to combat this type of problem. So from the graph, we can see that with the use of renewable energy sources, the amount of different poisonous gas which are harmful for our nature is decreasing day by day. But all renewable energy system, whether they are solar system or windmill, etc., they are totally incomplete with efficient storage system. So if we want to develop a good renewable energy system, then we have to develop an efficient storage system. In recent times, we are using different electrochemical storage system to store renewable energy. So electrochemical energy storage system that use chemical reaction or processes to store energy and use it. There are different such as lithium sulfur batteries, lithium ion batteries, lithium air batteries, or different metal ion batteries and supercapacitor. First, we would discuss about lithium ion battery. We all know that people have got Nobel Prize for their Nobel Prize in the field of lithium ion battery. Why lithium ion battery becomes so much important? With our needs, different electronic devices are becoming smaller and smaller in size. That is, we want portable devices for different applications such as digital cameras, mobiles, notebooks, computer. So to compromise such a good portable electronic devices, we need a storage system which will be efficient and portable. So lithium ion battery give us this platform. So from our mobiles to laptop, all we are using are constructed of lithium ion battery. In general, lithium ion battery have 4-layer structure. That is one cathode, which is generally made of lithium cobalt oxides, or sometimes using a current collector made of aluminum foil, a negative electrode or anode with a copper foil of thin current collector, a separator which are generally made up of a polymer film, and electrolyte material that generally consists of lithium salts. So from this structure you can see from anode and cathode there is some exchange of ion which was stored as energy in the lithium ion battery. So lithium ion battery principle depends on exchange of charge, mainly lithium. But lithium, we can use different types of lithium sources. Here we will see how nanotechnology, application of nanotechnology has benefited this battery system. If we use electrolyte that are made of nanoparticles, then it is easily, we can add this in solid polymer gel and enhance the conductivity and storage capacity of the system. Secondly, nanomaterials, as that property is different from the bulk one, we can increase their temperature resistance power and high stress application, which is very much important when we use this lithium ion battery in different vehicles. Also, the coating of the anode cathode, that also help us if we use nanomaterials or nanowires. The anode or maybe the cathode, we can increase the surface area of them, we can change the bonding of them, and the electrochemical reaction energy, which further increases the power capacity of the material. So nanomaterial is very much advantageous for lithium ion batteries as it increases the electron transport capacity, contact area. As we know that surface increases, that means the contact between the ion and the surface of the cathode or anode increases. This enables the realization that charging is done faster than usual conventional batteries. But there are some disadvantages also. We know lithium is an expensive material. So battery made of lithium ion is expensive, and every lithium ion battery required a protection circuit which is attached to the battery system. Several times we heard from newspaper, different social sites that there is an explosion in some devices which we are using lithium ion battery, because that in that case the protection circuit either does not stable or that is not working at that time. Aging effect is also very much responsible for degrading of a lithium ion battery with time, transportation problem, deep discharge, safety, that is safety, all these are related to the safety. So lithium ion battery are very much sensitive to temperature, so safety concern is very much important in case of lithium ion battery. And if the protection circuit of a lithium ion battery does not work, then that is very much harmful to the user. So people are thinking about some new system or device that can replace the lithium ion battery, or we can say the battery system. So in our future day, we will need energy for personal use, that is for mobile, laptops, etc., gadgets, and there will be also grid energy storage system. We all know fossil fuel are very much harmful for our nature, and we can use here a proverb about a minister of Israel. He said that Stone Age, before the Stone Age, end of stone, we have ended the Stone Age. So before all the fossil fuel are eradicated from this world, we have to move to a new energy system, that is renewable energy system. And to grow a good grid energy storage system without using battery, we have to use a new device or system which can store energy in grid energy storage system. That is, grid means all will give the energy to that, and when necessary we will use that energy system from that grid. Now, here are some comparison between battery and capacitor. We know there are two systems which can store energy. One is battery and one is capacitor. Now we have discussed about battery, we will discuss capacitor. So we all know capacitor means there is two parallel plate of conductor connected. There is some separation, we called it a capacitor. So in case of battery, the power density is high. For a general battery, it can store energy. That is, its energy density is high, but power density is not so good. And for a capacitor, power density is high, but the energy density is low. That means battery can store energy in greater amount, but the charging or discharging of a battery requires a good amount of time. Whereas capacitor can be charged or discharged quickly, but its energy system, the storing a capacity of energy of a capacitor is not so good. So we need a system where we have to increase both the energy density and power density. So battery has high power density, a low power density, we have to increase it, and capacitor has low energy density, you have to increase it. So we need to develop a device which has both high energy density as battery and high power density as capacitor. Along with that, it should be a longer life and its cost must be reduced. So supercapacitor is this type of electrochemical device which can have a moderate energy density, moderate power density, high capacitance value, and longer life. So nowadays we have seen that the application of supercapacitor, particularly in the automobile sector, are increasing day by day. Here we will look at the global market of supercapacitor. So from 2014 to 2022, we have seen that there is a probability of increasing the usage of supercapacitor. But the obstacle to grow are that the cost of the supercapacitor that are available in today's market are relatively high cost. They are getting a good competitive fight from the battery company, and consumer are sometimes they are conservative. We use a material when people told us that that is good. So if all few people are using that, a chunk of market share are confused to use this supercapacitor material. But in recent time, some new market opportunities in heavy electrical vehicles, smart grids, alternative renewable energies have forced the use of supercapacitor in world market as well as in India. So here we can see that in India, the usage of supercapacitor is also increasing at the rate of average 16% per year, because with the application in different sector, operation in a wide temperature range, and one of the property of supercapacitor help us, that is lifetime. So lifetime of a supercapacitor is greater than that of a battery. Here we can see two things, that is, one is Mahindra E2O car that is using supercapacitor. It is one type of electric vehicle, and the travel cost has reduced to 0.50 per kilometer. So it is too low, and with the increase of the price of petrol and diesel in India, we can say this is a great savior for the user. And the second one is e-rickshaw named Rahi. It is manufactured by Hero company. Its travel cost is 0.15 rupees per kilometer. So this is only two examples. In recent times, we will see more and more this type of vehicle in our Indian roads, which will decrease the amount of cost as well as the lifetime of that vehicle. But before going to all this discussion, we have to know what is supercapacitor, what type of material are used to develop a supercapacitor, and what we should focus in the research area of this field. So there are mainly two types of supercapacitor. One is EDLC, electric double layer capacitor, and second one is pseudo capacitor. In general, in today's market, all the available supercapacitor are made of EDLC type. In EDLC type, we use carbon-based materials such as graphene, carbon nanotubes, carbon foams, etc. And the second one is pseudo capacitor. In general, pseudo capacitor material are manufactured from conducting polymers or metal oxide. Nowadays, research is going on in this field, and till now there is no supercapacitor available in the market which use pseudo capacitor based material, but people are trying to do so because the capacitance of a pseudo capacitor is about 10 times greater than of a EDLC. We can also use hybrid type of supercapacitor that is using both material. Now, in electric double layer capacitor, there is no transfer of charge, but there is some quick process in where fast material are that is positive and negative ions are there, and that store the charges. In pseudocapacitor, there is a oxidation reaction which helps storing the charge by transfer of charges. And the third one is hybrid type of capacitor, where both pseudocapacitor and EDLC type of material are used. That is, if I use a anode of EDLC material, then the cathode will be of pseudocapacitor material. This helps to get a common type of capacitor which has high power density and energy density. Now, how we know that a material is a pseudocapacitor or EDLC of type? If we do the CV measurement of a material, that is current voltage measurement, then this is the graph. This green graph, that is a rectangular, this gives an ideal capacitor performance. If the criteria of the graph is like this red one, then this is EDLC type of capacitor. We can see also there this blue type of material, that is EDLC type of supercapacitor material. And now if there is some peak appear, that is like this black one, this peak appear, then this is influence of pseudocapacitance. That is the material which shows the property such as this type of graph, then we can say that this is a pseudocapacitor types of material. Our aim is to prepare a material of these pseudocapacitor types. Now, as I have told previously, that is, for a battery, energy density is high, whereas for capacitor, power density is high. So this blue type area is of supercapacitor material, where they have moderate energy density comparable to the battery and moderate power density comparable to the capacitor. So supercapacitor, the advantage of supercapacitor is that it takes only few seconds to discharge or recharge, and the recharge cycle is up to 1 million, that is 10 lakh times it can be recharged with a service life of 15 years. If we can acquire this type of property for a low cost material, then the cost of electric vehicle using supercapacitor will decrease by a large amount. Now, as I have told you previously, that is supercapacitor has different application in industrial sector, electronics, power sectors, in day-to-day life, computers, scanners, smoke detectors, etc. But it has also some disadvantages. That is, the amount of energy stored per unit weight is considerably low in today's supercapacitor material. And the voltage also for a material which store energy, the voltage also vary, which is very much harmful for a material to use in different applications such as laptops, mobile, etc. So we need a stable voltage supply for application of supercapacitor in different devices. Now we'll see that how a good supercapacitor material need high power density, high energy density, high specific surface area, high porosity. That means the gap will be some of better extent, and size. We can say that nanomaterial are very much advantageous for this, because if we can decrease the size of a material, then surface to volume ratio increases, which gives us high specific surface area. And thing has a good conductivity, then it is. So you in brief one of our work capacitor, we have obtained a nickel oxide thin film for. So we have chosen nickel oxide.
Okay, there is some network problem from the speaker's side. So keep your patience for a few moments. It will be solved soon. Thank you.
The structural analysis also shows that it is a nickel oxide material. I am not discussing detail about that. And surface morphology confirm that is a porous material. So two property we have obtained, that is low cost, and the second one is porous material. Third one is that is cyclic voltammetry analysis. This is important for a supercapacitor material. See here, this curve shows that the property of this material, there is the peak, and we can see this is of pseudo capacitor type of material, and the maximum specific capacitance value of this type of material is 1341 farad per gram. So the theoretical value of the specific capacitance is of nickel oxide is about 3500 farad per gram, but here we have obtained 1341 farad per gram. So there are miles to go to achieve theoretical value, but this value is also of good, and we have also rechecked it from galvanometric charge discharge process, which also give about 900 farad per gram. And the main important thing is that after 1000 cycle, the capacitance retentivity is about 90%, which is also good one. That means if we use this material in a supercapacitor device, after 1000 or 10,000 cycle, we can regain a value of that capacitance. This is also published in well-known one of the journal, that is Electrochemical Acta. But these are in a lab condition. To convert this type of material to devices which will be applicable in the practical purpose, there are different things we have to obtain, and that is a very good, I can see a tough job to be done. So for oxide, I have seen that I use nickel oxide. I have also value of the capacity. Now, a vital answer is that combining battery with supercapacitor is also answer. None the battery, none the supercapacitor is good one. That is, we have to combine this, and that hybrid system is good. Suppose we are using a battery which has high capacity but is slowly charged. Now we use it in a vehicle. To charge the vehicle, we will need about 10 to 12 hours per day. So it is impossible. Now, in supercapacitor, it will charge or discharge fast, but its capacity is low. So we have to combine this system, and we have to develop a hybrid system that will be higher capacity, faster charging discharging rate, lightweight, flexible. In different renewable energy sources, what we are doing in power grid, we are using both battery and supercapacitor material. In also vehicle, that is hybrid electrical vehicle, or that is also heavy electrical vehicle, we also call them. There we use both battery and supercapacitor. Suppose a car is running at a constant speed. At that time, we use the energy of a battery. When we need to break it, that is, you have to start or we have to stop it, then we use the power of the supercapacitor. So nowadays, all the system we used hybrid battery and supercapacitor system. So to convert all these system from battery to supercapacitor, we need or we have to enhance our funding or in the supercapacitor material. In we can say in nanotechnology, using nanotechnology, that is nanomaterial, maybe 1D material, 2D material. There are several material, and there are several process which we can use to grow those material. Our only need is to develop a large surface area, high pseudo-capacitance and high energy density material. What I want to tell that after 10 to 15 years of enhanced research of supercapacitor material, there is none a good devices which can replace the battery system with supercapacitor. So we are using a stopgap system, that is the system using both battery and supercapacitor. Now our work is to replace the battery with a good type of supercapacitor material. So what we have to do? We have to give a lot of funding, lot of concentration to the supercapacitor research. First, we have to choose different type of nanomaterials or different types of material. We have to grow them we have to process either nanomaterials or thin film with different physical and chemical process. Then we have to characterize it with XRD, same, TEM, weight for porosity, cyclic voltammetry. This is important method by which we get the specific capacitance of the material, and then galvanostatic charge discharge process. We have to check whether the result of this cyclic voltammetry is of practical use or not. Then we have to see the graph. Our main concern will be to grow a pseudo-capacitor material. So if the material gives this type of graph, then we have to use that. There are several research labs in India that are working in this field. Few of them are IIT Roorkee Department of Physics. We are also from Indore IIT, Department of Chemistry from IISER Bhopal, Jadavpur University IINST in Mohali. All you can contact them for this work. Thank you.
Thank you, sir. For
Anyone have any?
Okay, for such a nice representation. Thank you. Now I would like to ask the participants if they have any questions. Please raise your hand. We will unmute you. Any questions from participant side?
I think there is some internet problem in the middle of the lecture.
Yes, for a few moments. No problem, sir. All over the connection was good. So from Dr. Mukherjee's lecture, we came to know about the basics of lithium-ion battery and their advantages and disadvantages. Dr. Mukherjee has beautifully portrayed the both. The next generation storage system will be supercapacitor with high energy density and power density. So from the discussion of Dr. Mukherjee, I think now we are all well aware of the next next generation next generation energy storage devices. Thank you, Dr. Mukherjee, for your such a nice presentation. So no more questions from the participant side. So we will move forward for our next session. So our next esteemed speaker is Dr. Manisha Bajpayee, who is an assistant professor of physics from Bihar University, Muzaffarpur. Her title of the talk is Application of Columnar Mesophysics Structures in Photovoltaics. So Dr. Bajpayee has done her graduate and postgraduate from BNB College, CSJM University, Kanpur. She obtained her PhD with specialization in organic electronics from Banaras Hindu University, Varanasi, in association with National Physical Laboratory, New Delhi, India. She has more than 3 years of postdoctoral experience from University of Allahabad, India. She has published 20 international journals. She has also authored one textbook entitled Laser Systems and Applications from Wiley. So now I would request Dr. Manisha to start her presentation. Ma'am, please unmute yourself. I would request Dr. Manisha to unmute yourself.
Yes.
Thank you, ma'am.
Thank you, Mala, for such a nice introduction. I am very much thankful to you and your team for invitation in the webinar on the current status and future scope of the nanomaterial and technology. Now I am going to discuss about the application of columnar mesophasic structure in photovoltaics. As we all know that the rate of energy consumption is essential for progress of our civilization, and therefore main problem is how we produce energy. Therefore, two type of energy resources, that is renewable and non-renewable energy resources. Renewable are man-made and non-renewable are the energy resources available on our earth, that are crude oil, fossil fuel cells, etc. But we have already seen that there is the shortage of oil and price is already increased continuously. Also, if we talk about the fossil cells, the era of non-renewable energy resources, it is also going decrease. Oil and natural gases are also depleting. Also, excess use of fossil fuels and nuclear energy has created bad impact on environment, social and sustainable problem. So we need such energy resources that will be forever and can be used without pollution. well, so larger than the present consumption rate of all energy resources. Therefore, we use such renewable energy resources as an alternate energy resources, and the device that is used to convert the solar energy into electrical energy is called photovoltaic solar cell. Photovoltaic solar cells are basically semiconductor diodes, PN junction diode, in which semiconductor material is sandwiched between two metals. Basically, in organic solar cells, silicons are used in inorganic solar cell that are really reliable and environmental friendly. And all over the world, approximately 40% efficiency have been achieved in tandem structure, but their application in the commercial purpose is limited due to their large area installation and production temperature. So researchers have moved towards organic solar cells. Organic photovoltaic solar cells are based on organic materials that perfectly suits as their process is easy. They are large area flexible and flexible. They are lightweight, and they are also cost effective. But application of organic solar cells are limited due to their low efficiency, strong binding energy of excitons, low charge carrier mobilities, as their mobilities ranges between 10 power minus 3 to 10 power minus 5 centimeters square per volt second, and their short exciton diffusion length, that is ranges between 5 to 10 nanometer, and their poor stability. So still researchers is going on to overcome these problems. These are the basically polymer solar cell materials that are basically used in the fabrication of polymer solar cells. Polymer solar cell is a semiconductor PN junction diode in which active layer, that is the polymer blend of donor and acceptor material, is sandwiched between the electrode, anode and cathode. These are the donor material, that is MDMO, PPB, P3HT, also PCDTBT, PTB7 are also used as donor material, and PCBM and their derivatives are used as acceptor materials. If we talk about the working principle of the OPV device, that is to convert the electrical energy from the solar energy, that is described by the three steps, that is absorption of light leading to the formation of an exciton state, that is called electron hole bound pair and also called exciton. Next, the dissociation and their diffusion of exciton into free electrons and holes, and next the transportation and their collection of charge carrier to their respective electrodes. Since the absorption efficiency of organic materials as high as much only 100 nanometers thickness is enough to absorb most of the photons, so carrier collection efficiency increases as well. However, most of the organic materials have band gap greater than 2 electron volt, that is 620 nanometer. So it limits the possible harvesting of the solar photons up to the 30% efficient solar cell. Therefore, we have to improve our band gap of the hole transport material as well as electron transport material, that are acceptor and donor. Critically, solar cells is characterized by its power conversion efficiency, that is totally depends upon the fill factor. fill factor is determined by charge carrier reaching to the electrodes when built-in potential is lower towards the open circuit voltage, that is VOC. The fill factor is defined as the IMP into VMP over ISC over VOC, where VOC is the open circuit voltage, ISC is the short circuit voltage. Sorry for interruption. We can see here the JV graph, ideal JV graph to determine the PV parameters. Here we can see VOC and JSC, and P maximum defines the fill factor, and the efficiency of the solar cell may be defined as fill factor into VOC into ISC over P light. That is, input light comes onto the device. That means the product VOC into ISC into fill factor defines the maximum efficiency of the solar cell. So we have to improve the product VOC into ISC into fill factor to improve our efficiency of the solar cell. Moreover, charge carrier mobility and energy band gap. So to improve the efficiency of the solar cell, we have to improve our basic transport parameters of the materials used in the solar cell. Now I will discuss about the liquid crystal. Actually, I will not go into detail about the liquid crystal. As we all know that there are basically three states of matter, that is solid, liquid and gas, and liquid crystals are the fifth state of the matter. These are the states substance that blends the structure and properties of normally disparate between the liquid and crystalline solid states. In the solid state, there is a particular anisotropy, and if we talk about the liquid material, there have some certain properties, for example, drop formation, viscosity, and so on. But in liquid crystal state, there is a intermediate state between the solid and isotropic liquid state. So we can say that the distinguished characteristic of liquid crystal state is the tendency of the molecule to point along a common axis called the director. This is in contrast to the molecule as compared to liquid phase. We have no intrinsic order in the liquid state, but in solid state, molecules are highly ordered and have little translation freedom. The characteristic orientational order of liquid crystal state is between translational solid and liquid phase. This is the origin of mesogenic state. Some of the applications of liquid crystal are physical and biological, that are liquid crystal displays, liquid crystal thermometers, optical imaging, and some also liquid crystal application in the organic electronics, that are organic photovoltaics, organic light emitting diodes, also organic thin film transistors. Some researchers are used liquid crystals in organic electronic devices. These are the biological applications of the liquid crystals. This is the one of the most important category of the liquid crystal. These are the typically a rigid aromatic core and flexible peripheral change, and a good material for organic solar cell as a whole transporter due to its high electron affinity and high exciton diffusion length, their mobility and fluidity. In our approach, we have used PCDTBT, that is poly and heptadecanal carbazole trimethyl benzothiodiazole as a donor material, also called whole transport material, and PC70BM, that is phenyl C70 butyric acid methyl ester, used as acceptor, that is electron transport material. And we have used a despotic liquid crystal material, that is hexabutane butyloxy thiphenyl, that is HAT4, as an whole transport material. Its electron affinity is very high, that is 2.3 electron volt, and we have used in our study P.PSS, that is polyethylene dioxythiophene, polystyrene sulfonate, and molybdenum trioxide MOO3 as a buffer layer, and aluminum as a cathode. This is the schematic of the device that we have prepared. We have prepared actually 14 devices in our study. We have used P.PSS and MOO3 as buffer layer, so we named them device A and device B respectively for the P.PSS and MOO3 with the different thicknesses of HAT4. This is the JV graph showing PV response, and their parameters are also shown in the next slide. But here we can see that short circuit current increases continuously sorry for hurdle. Here we can see the JV graph showing the PV response. We can see that the JSC increases continuously from device A to A5, but is going to decrease above 30 nanometer, and same pattern has been observed in the device B. This may be due to the device thickness. As the device thickness of the device increases, there are the parameters to decrease the film of the degradation of the film, so overall the performance of the device, and also the mobility of the charge carrier. As we all know that the child law, J is proportional to V square over D cube. As we increase thickness, the charge carrier mobility decreases, and overall the performance of the solar cell or any devices will decrease. These are the photovoltaic parameters for device A and device B respectively. Here we can see that we have achieved maximum 2.66 power conversion efficiency for the set A devices, where we have used P.PSS as a buffer layer, and efficiency of 4.18% has been achieved for the MO3 devices as buffer layer. Also, we have performed the annealing response of the HAT4 coated silicon substrate, and finally the solar cells. We can clearly see here that the devices with thermal annealing show better performance than without annealing of the devices. Maximum efficiency of 5.14 we have achieved with this exercise, and this is the substantive improvement over the previously reports. For example, Vacuum et al., they have reported that the thermal annealing was not effectively worked in PCDTB and PCBM blends solar cell. So we have performed the annealing of the So we have performed the annealing of the silicon annealing of HAT4 film on the silicon substrates, and we have overall we can see that the morphology of the HAT4 after annealing temperature at 100 degrees centigrade increases. Actually, at high temperature, HAT4 possesses hexagonal mesophase when it is of column further improves, and therefore this work has been published in an international journal, Liquid Crystal. You all can read this paper from this link. Thank you so much. Sorry, Mala, for the so much
problem,
interruption during the talk. Actually, one of my faculty is interrupting, calling
Okay,
many
ma'am, no
times. Sorry once again.
No problem, ma'am. Ma'am, please stop sharing your screen.
Yes, please.
Okay, thank you, ma'am. So thank you very much, Dr. Manisha Bajpayee, ma'am, for
you,
her
Mala.
beautiful explanation about solar cells, basically organic solar cells. Now we will take questions from the participants. So if anyone has any questions, please raise your hand. I will unmute you. I am requesting the participants for questions, please. Okay, the field is quite new. Solar cell itself is a new field, and organic solar cell is newer than that. So, ma'am, my question to you is that, is organic solar cells already available industrially in market?
Yes, Mala, organic solar cells are easily available in the market. Actually, we can see that Samsungs are producing devices based on organic solar cells, and one other company from Japan, I don't know that name, and also produce some products based on organic solar cells, organic devices are easily available, but actually their cost are so much. We are working with their cost, so not easily available, but they are researchers are working on the organic solar cell and their devices, some devices.
Okay, so I think in near future, India will also produce organic solar cells because there are so much advantage in organic solar cells. Ma'am, can you please tell us what is the approximate thickness of this type of cells?
Sorry, Mala. In NPL,
the average
in
size,
National Physical Laboratory, where I
you were not audible, ma'am.
so sorry, Mala.
Okay, ma'am. Please continue.
In National Physical Laboratory, in our lab, where I worked, my research work during PhD and postdoctoral also, their 11% efficiency they have achieved in lab scale. But commercially, it is not available in India, as we can see. Yeah.
So we can collaboratively work, especially from physics background and chemistry background people to achieve such type of solar cell, which is very much good for the renewable energy.
Yes, ma'am. Please. Yes.
Okay, thank you, ma'am.
Are you talking about some collaboration with some?
So I will actually, in this platform, I will appeal to all of the faculty members, the student researcher, to focus on the new type of nanotechnology research and especially the collaborative research, because all the research we can't do alone. More and more collaboration will actually.
Yes, Mala, you are right, Mala.
Okay, thank you, ma'am.
Okay, thank you.
Now we will proceed towards our next lecture. Our next speaker is Dr. Dheeraj Kumar Pandey. He is an assistant professor of physics from Alien Mahila University, Darbhanga. So, Dheeraj sir, I will ask Professor Dheeraj Kumar Pandey sir to unmute yourself.
Hello, ma'am.
Okay.
Am I audible?
Yes, you are audible. Very welcome to the webinar, sir. So, Professor Dheeraj Kumar Pandey, sir, has research specialization mainly in condensed matter physics, that is the solid state physics, and computational nanoscience and nanotechnology. Dr. Dheeraj Kumar Pandey, sir, has done his PhD from University of Allahabad. He has published a few international journal publications related to nanoscience computation. So thank you, sir, for joining us. I will request Dr. Dheeraj Kumar Pandey, sir, to start his presentation. Thank you, sir.
Thank you, ma'am, for such a nice introductions. And I am sharing my slide here.
Okay, sir, please share your slide.
It's here.
Sir, your network bandwidth is low. It's not till shared. Sir, in that case, you can use your mobile also.
1 minute, it may be connected.
Yes, sir,
Now, is it here? My slide?
No, sir.
Okay, 1 minute.
So till now, we have talked about mainly the experimental background of nanoscience and nanotechnology and its application. And this talk is about the computational nanoscience, that is the theoretical background. So I think all of our participants will be benefited because to perfectly conduct and to perfectly know something, some subject material, it's the theoretical and experimental, both works are mandatory and necessary. In the meantime, I would like to ask all the participants, the faculty members, the students, to fill the feedback form for today, the day 2. It's already given in the chat box. Please check it and fill the feedback form. It's mandatory for the e-certification.
Is it shared?
No, sir.
Ma'am?
So you can just mail it and I will share it if it's possible.
Yeah, I can mail you.
I will request our participants to fill the feedback form and comment so that we can organize more webinars related to physics and what are the interesting topics to them. And if they want some more basic speeches or talks related to nanotechnology and nanoscience, that will be very much helpful for us, that is the organizers, to conduct such webinars. So since webinar is totally online, there may be some internet problems, and that's why sometimes causes some interruption. So I think our participants are patient enough so that we can smoothly continue. Thank you everyone for your patience. I'd request our next speaker, Dr. Dheeraj Kumar Pandey sir, to just mail me the PPT so that I can share it from my screen.
just a minute, I am sending you. I am also trying to share, but it is
So
showing
because
some
of the
error.
low bandwidth, it's not visible from our side, sir. I think that's not a problem because science needs a lot of patience to invent or discover something new.
Ma'am, I have sent PPT. Please share your side.
Okay. Sir, have you sent it to my Gmail account?
It is still working. I have sent, but still working.
Okay, sir,
It
no
is
problem.
slow. That's why.
No problem, sir. But in the meantime, I will request you to just say us about the background of this computational nanoscience. And meanwhile, we will start your presentation. Sir, in the meanwhile, I would like to request you to tell us about the background of this computational nanoscience. Sir, you can start. Meanwhile, we will share the PPT.
Ma'am, hello.
Yes, sir.
Is my slide is shareable?
Yes, yes,
Shared?
yes. I am sharing it in a few moments.
Okay.
Sir, is it visible?
Yeah. Just only make it full slide. I think.
Okay, okay. Is it okay, sir? Is it okay now, sir? Sir, please unmute yourself.
Okay. May I start?
Yes, sir, please start.
Okay. Thank you, ma'am, and sorry for interruptions. And the topic of my presentation is here, computational study of nanomaterial. And firstly, I want to thankful to the principal of organizing college and Mala ma'am to inviting me for presentation in this seminar. And myself is Dheeraj Kumar Pandey, assistant professor in RV College, Dalsingsharai. Next slide, ma'am. Hello. Hello.
Yes, sir, next slide. It's not working in the full screen mode. Yes, sir.
So this is the section of this is the sections which includes of my talk, and I have divided in 4 sections. First is the introduction with the nanoscale word, that is the nanoscience and nanomaterials, and second section is about the density functional theory that led behind the computational study, and third sections will be the different types of computational techniques which are used by the researchers at the present scenario. And at last sections, that is about the zinc sulfide nanoclusters, which is a system which is used by the computational techniques to explore the properties. Next slide, please. So I am starting in first sections, and usually I will introduce with the nanometers. As you will know that is in length scale, a nanometer is a 1 billionth of a meter. That is 1 meter equals to 10 to the power minus 9 nanometer. Sorry, 1 nanometer equals to 10 to the power minus 9 meters, and usually at present. The scientists are using a scale, nanoscales, and it is not a particularly defined, but still it is known as up to 1 nanometer to 100 nanometers. It is considered as a nanoscale range. Next slide, ma'am. Usually, present scenario, there are 2 famous words, that is the nanoscience and nanotechnology. In nanoscience, usually researchers are exploring the chemical and physical properties of the material up to 100 nanometers, and the materials which size or at least one of its dimension lie inside the range of nanoscales, that is considered as a nanomaterials or nanostructures. And with the help of these properties, fabrication of new products and devices deals under the nanotechnology. One of the example we can see that in nanoscience, people are researchers are predicting the properties of the materials, and then further they are utilized in the production of fabrications, and with the help of fabrications, then it are used in producing the clothes like trouser. Next slide, ma'am. So in this slide, I want to visualize the length scales of nanometer range. Usually, we know that the bore radius is about of 0.5 angstrom, that is 0.05 nanometers, and a carbon atom has a van der Waals radius about of 0.7 nanometers. Means its diameter will be 0.34 nanometers. So if we arrange carbon atoms in a line of 1 nanometer, so we require 3 carbon atoms. And if we put in a two-dimensional surface of 1 nanometers, then we require 9 carbon atoms. And if we put carbon atoms in a three-dimensional of 1 nanometer side, then it requires 27 carbon atoms. And up to the maximum nanoscale range, that is the 100 nanometer range, then it requires 2.7 into 10 to the power 7 carbon atoms. While in the case of bulk of 1 meter cubic systems, it requires 2.7 into 10 to the power 28 carbon atoms. Means in nanoscience or nanomaterials, we are dealing with the number of atoms which are less than 10 to the power minus 21 carbon atoms in comparison to bulk materials. Next slide. The foundation of nanoscience and nanotechnology is already established or indicated by the famous physicist Richard Feynman in 1960, and by his famous quote that there is a plenty of room at the bottom, which means that every materials can be subdivided into a large number of materials or atomic levels, which has independent identity, and each represents the individual structure or atoms. Next. So we easily see that nanoscience is not only the biology, not is a physics, and not is a chemistry, but includes all the sciences which deals with the object or substances which are very small sizes. Next slide. So what is most interesting thing about these nanomaterials are in this size regime, that is the materials properties change very abruptly. Means which material in bulk phase behaves like as a bad conductor or perfect insulators, but it is behaves very differently in nano range. So all the materials have becomes a candidate in nanoscience for study purpose and for also application purpose. And all these properties depend upon two parameters, that is the size and shape. Because when size or shape change, their physical properties also change. A simple example, next slide, ma'am. A simple example can be seen that in bulk phase, gold appears in yellow colors. But when we deal in nano range, then its color changes. It appears in red color. It is because of the electrons in gold particles that are confined in a very small range, and that's why their properties change. Next slide. So in nano range, some effect arises because of the properties are non-smooth wave change, because of quantum confinement effect. Because in such a nano range, classical mechanics is not able to explain the properties. So a new mechanics is introduced, that is the quantum mechanics, which usually based on the wave functions. It considers that the system is defined by a wave functions, and if we measure the accurate wave functions, then we can find all the properties of that particular system. And when this wave function is affected by the size, then all the properties of that particular system also change. Next. Another effect is arises in nano size range, that is surface to volume ratio, that becomes too much high. If we take the examples of 1 meter cubic systems, then it has a 6 surface, and that will be area will be 6 meter squares, and its volume will be 1 meter cube, but when it is subdivided, start to subdivide it into eight cubic systems, then its surface area increases and becomes 12 meter squares, and it is further subdivided into 27 parts, then it becomes more surface area. This surface area also increases, so it becomes the more important in the nanoscience because catalyst has more option to react with the materials. Next. So with these two effects, the property change in very non-smooth way. That's why in present scenario, nanoscience has become more interesting research for the students and also for the researchers. And it has been revolution. It has been create a revolution in all sectors like aerospace, agriculture, biotechnology, homeland securities, energy, improvement, and information technology, and etc. Next. Second section, that is the density functional theory. That is a theoretical approach, and now the computational techniques are basically based on the density functional theory, and this type of study is known as ab initio methods. Ab initio, that is a Greek word, and it means that is a first principle study. In this type of study, we does not require any experimental data or any experimental results. We just require the number of ions present in that particular atom. Means, suppose that we want to produce a system of zinc oxide nanomaterials, and we want to predict the properties of zinc oxide nanomaterials. Then we just require the number of ions present in the zinc atoms and oxygen atoms. That gives the total properties of that particular material. Next. This theory is based on the quantum mechanics, and quantum mechanics is basic equation that is known as Schrodinger wave equations, given by x psi is equals to E psi, where H is the Hamiltonian, E is the eigenenergy value, and psi is the wave function of the systems. And that's why this theoretical techniques or this theory is also known as quantum mechanical modeling. Next. In this theory, system means what will be the nanomaterials. It has been considered as a system, and this system is considered as a many electron systems. And in such many electron systems, the Hamiltonian can be written as the sum of the two parts, that is the kinetic energy and potential energy. And this potential is very difficult to calculate in such a large electron systems. So very important to predict the properties in this using this theory, that is the effective potential to calculate. If we calculate effectively the potential energy, then we can easily find the eigenvalues and eigenfunctions of that particular system. Next. By using this quantum mechanics basic equations in 1964, Bhawan and Kong produces this density functional theory. Next. So in density functional theory, the ground state energy of any system is considered as a function of the charge density. We can see that the energy of any system is the sum of the three types of energy. First term represents the kinetic energy, second term represents the interaction energy with the external potentials, and third term represents the electron-electron interaction energy. This electron-electron interaction energy is further sum of the two types of energy, that is the electron interaction energy with the neighboring electrons, and second term, that is the exchange correlation energy. In second equation, the last term, that is the exchange correlation energy, that is very difficult to measure accurately. If we measure accurately the exchange correlation energy, then we can easily find the properties of a system. Next. Next time.
Sir, please unmute yourself. Sir, please unmute yourself. Dheeraj sir, please unmute yourself. There is some internal error.
May I add one, ma'am?
Yes, sir, you are audible. So please proceed.
So this exchange correlation energy has several approximations. First approximation was introduced as a local density approximation, in which the local density energy is a function of only of charge density, but it has several limitations, so it requires another approximation, that is generalized gradient approximation. That is the improved approximation. In this approximation,
So I would request our participant to be patient. There is some internal problem from Dr. Dheeraj Pandey's side.
hello.
Yes, sir. Yes, sir, sir. Please continue.
Your weather is not good. It is
Okay,
raining
sir, no
here,
problem.
heavily
Please
raining.
continue.
That's why I think net problem. Okay. So another improved approximation, that is the generalized gradient approximations, in which exchange correlation energy is considered as a function of charge density as well as its gradient. But this approximation is also has several limitations. So it requires a next slide, ma'am. So it requires a new approximations which overcome the limitation of both approximations, LDA and GGA. At last and present, that is a hybrid functionals is introduced, and this is the latest approximation. Previous diagram, okay. So in this approximations, Lee, Young, and Parr, three scientists have made the modification in Becky's three parameters, and also included local density approximations as well generalized gradient approximations. By using this B3LYP approximations, we can get better properties, we can get better values, yeah, and eigenenergies of the system. Next. So this density functional theory has also limitations. It predicts only the properties of ground state But for excited states, we have to require time-dependent density functional theory. In time-dependent density functional theory, the time-independent Schrodinger equation is replaced by time-dependent Schrodinger equation. Next slide, ma'am. Now that is the section 3, which contains the computational techniques. Okay. At present time, people are using many of codes for predicting the properties like Gaussian, Orska, ADF, Molapro, NWCAN, and GAMS. These has several codes which are used by the researchers to predict the properties with the help of computational. Next slide, ma'am. Next, ma'am. Next slide. So, in 1960, John Copley and his workers have used a Gaussian code. Presently, its latest version is Gaussian 16. And with the help of this computational codes, we can find the several physical properties like we can, next slide, ma'am. Next. With the help of Gaussians, we can optimize the geometries of the nanostructures. Then we can calculate the energy and other properties like vibrational frequencies, molecular orbitals, dipole moments or multipole moments, spectroscopic parameters like NMR, EPR, etc., and polarizability. Next. So, with the Gaussians, we can predict the properties, or any computational codes, we can predict the properties which experimentalists cannot be easily done. So, if we can calculate the properties or explore the properties of nanomaterials, so it will be a task for the experimentalists to produce them. Next. In section 4, I have taken a system of zinc sulfide nanoclusters with the computational techniques to explore its properties. First, nanoclusters is what is a nanocluster? Usually, a nanocluster is a zero-dimensional structure. Means if we divide the nanomaterials on the basis of dimension, so 0 dimensions, 1 dimension, and 2 dimensions. 2 dimensions usually a thin films, and 1 dimensions usually a nanowires and nanotubes. And in 0 dimensionals, that lies in nanoclusters. Nanoclusters we have defined a non-periodic 3-dimensional structures, and it is an intermediate state of matter between molecule and bulk. The most important things about the nanocluster is also their property change in very non-smooth way. When the number of atoms change in nanoclusters, their properties also change. So we have chosen here zinc sulfide materials. Usually zinc sulfide material has a wide direct band gap semiconductors having 3.65 electron volt. A bulk May I audible, ma'am?
Yes, sir, you are audible.
Yeah. Zinc sulfide material has several potential application in fabrication of optoelectronic devices. So it is a significant material and also can be studied in the nano range. Next. So here is the start our calculations with the help of computational techniques, and I have used Gaussian 09 codes for predicting the properties of zinc sulfide nanomaterials up to 2 to 5 atoms. Means that materials will be composed from zinc and sulfide atoms, and the sum of both the atoms will lie in the range from 2 to 5 atoms. First of all, we have tried to find the most stable structures of zinc sulfide atoms up to 5 atoms. then we have tried to find out the properties, their electronic, vibrational and optical properties. Next slide, ma'am. So this is the figure of nanoclusters. We have model for 2 atoms and 3 atoms. So for 2 atoms, we have just only one candidate, while for 3 atoms, there are 2 configurations, ZnS2 and Zn2s configurations. Each ZnS2 and Zn2s configuration has 3 candidates for its configurations. Next slide, ma'am. This is all the optimized structures of ZnS3 configurations. In these configurations, we have taken 1 zinc atom and 3 sulfur atoms. And we have chosen different types of structures which can be possible. Next. This slide contains Zn2s2 configurations and Zn3s configuration of the nanoclusters. We can see that only 2 stable structures are possible for Zn3s configurations, while for Zn2s2 configurations there are 5 candidates. These clusters, nanoclusters, are arranged in decreasing order of the binding energy, or you can say the decreasing order of their stability. Next. Next, ma'am. Yes, this is a ZnS4 configuration which is containing 5 atoms, and it has also 4 configurations. Means one is the ZnS4 configurations and others are Zn2s3, Zn3s2 and Zn4s configurations. Next. These are all optimized structure for Zn2s3 configurations. In this configuration, pentagonal one structure has highest final binding energy, and planar structure has lowest final binding energy, and pentagonal is also considered as most stable. Next. This is the Zn3s2 configurations, and it has 7 stable structures. Next slide, ma'am. This would be the probably last structures, last slide of the structures which have totally I have modeled, and it is containing 5 atoms in which 4 Zn atoms and 1 sulfur atoms. So all these are total 46 different type of stable structure of zinc sulfide up to 5 atoms, and we have taken different type of structures including linear chains, planes or 3-dimensional structure for obtaining the stable structure. In this way, the system energy is converted to 10 to the power minus 7 milli electron volt, and forces on each atom is considered up to 10 to the power minus 3 electron volt per angstrom. Next slide, ma'am. After all, the basic of considering the most stable structures, we have chosen binding energy, and binding energy we have calculated by subtracting the total energy of a nanocluster from the sum of the energies of the isolated atoms present in that particular nanocluster, and the resultant quantity is further divided by the total number of atoms, and we name this as a binding energy per atom. We have also calculated 0-point energy, and this 0-point energy is further subtracted from the binding energy to obtain final binding energy, that is FBE. Next slide, ma'am. So, for each size that is represented by N is considered on the basis of final binding energy, but one parameter is also necessary, that is the real vibrational frequency. if any structures which has a higher final binding energy or higher final energy, but its vibrational frequencies are imaginary, then that structure is considered as unstable. So real vibrational frequency must be required condition for stable structure. Next. This is the total data, and also further in slides, on the basis of which I am describing that which structure is most stable or unstable. We can see that for zinc sulfide only one candidate is available, and this is considered as most stable, and our calculation are very close with the others. Others means others researcher have also calculated with other code, and we are very close to them. In ZNS2 configurations, we can see that there are three different types of candidates. Linear ZNSS has highest final binding energy of 1.54 electron volt, but this structure has imaginary vibrational frequency. That's why it is considered as unstable. So next candidate, linear ZNS, is considered as a most stable structure. For ZN2S configurations, linear ZN is considered as most stable because it has the highest final binding energy. This table includes the symmetry of the structures as well as ground state multiplicity, binding energy, 0 point energy, and then final binding energy. And we have also presented here the HOMO-LUMO gap of all these stable structures. Next. This is the total 4 atoms structures in which we can see that in ZNS3 configurations, rhombus, bent, and triangular planar structures are considered as unstable because their frequency will be imaginary. And next candidate was pyramidal, that's why it is considered as most stable. In ZNS2 and ZN3 configurations, rhombus and trizonal structures are most stable structures. Next slide, ma'am. In 5 atoms, first 2 configurations, we can say that pentagonal in ZNS4 configuration is also unstable because of its imaginary vibrational frequencies. But for ZN2S3 pentagonal 1, there are 2 pentagonal configurations are possible. That's why pentagonal 1 was considered as most stable. Next. So last 2 configurations for 5 atoms, ZN3S2 and ZN4S configurations have pentagonal and trapezoid structures because of their highest final binding energy, and there is no candidates is available having imaginary vibrational frequency. Next. This is the table which contains the vibrational frequencies and infrared intensities, relative infrared intensities, and Raman activities. We can see that in 3 atoms configurations, linear ZNSS has imaginary vibrational frequencies, which is shaded in blue color. It represents that imaginary vibrational frequencies. So this structure was considered as unstable. Next slide. Here also 3 structures, rhombus ZNS3, bent ZNS3, and triangular planar ZNS3 are also considered as unstable because there at least one of frequencies are imaginary. Next slide, ma'am. It is also containing the data of vibrational frequencies, and only one ZNS4 configuration is also considered because their 2 vibrational frequencies are imaginary. So next candidate was become the candidate for the most stable structures and also for the last one. Next slide, ma'am. Okay, this is the last one. Pentagonal and trapezoid structures, none of them has vibrational frequencies. All frequencies are real. So these will be stable structures. Next, ma'am. So most important and interesting thing is that the variation of the final binding energy, how the variation is taking place. So from these tables, and we conclude that which are the most stable structures, and then we try to obtain this variation, and we found that as the number of sulfur atoms increases, the value of final binding energy also increases. The nanoclusters containing maximum number of sulfur atoms are considered to be the most stable structures, and final binding value is also increases with the nanocluster size. Next slide, ma'am. This is the table for the charges on atoms and dipole moments of only most stable nanoclusters. So all these data are calculated by the Gaussian codes. Next slide, ma'am. This table confirms the study by computational techniques, because we can see that after a rigorous study of the properties of these materials, we find that only most stable structures and their optical properties, in which excitation energy and oscillator strength, we can see that our most stable structure for 2 atoms, linear ZNS, and for 4 atoms, Zn2S2, rhombus structure, their excitation energy are very close to the experimental data which are presently available. It means our theoretical study are very much accurate, are very much close to the experimental results which has been found by the experimentalist. Next slide. So these are the optical spectra only for the most stable structure, for obtaining that their spectra is lying mostly in the ultraviolet range. Very few of them is lying in the visual range. Next slide, ma'am. This is also the optical spectra only for most stables. One more slide. Next slide will be also, I think, will be represent, yes. All these spectra for the only for most stable structures. Next slide, ma'am. So finally, on the basis of this computational technique study, we conclude that for zinc sulfide systems, the nanocluster containing maximum number of sulfur atoms for each size is most stable in comparison with the other nanocluster of the same configurations. Second conclusion is that the final binding energy of most stable nanoclusters also increases with the nanocluster size. Homolumogap variation also shows that up to 3 atoms it decreases, and after that it increases. IP and EA means we have also calculated ionization potential and electron affinity. We show a zigzag behavior. Next slide. So most of the nanoclusters, the absorption spectrum is quite weak in visible region, but that was strong in ultraviolet regions. And few of the nanoclusters have highest final binding energy, but still they are considered as unstable because of their imaginary vibrational frequencies. So finally, I think this is the total study of my this system for zinc sulfide with the help of computational techniques. And with the help of computational techniques, we can obtain or predict that properties which beyond the experimentalist, means which experiment cannot be performed, but with the help of computational techniques we can easily predict their properties. And if these properties are very useful or application point of view, then it will draw the attention of experimentalists. That is the main application of these computational techniques. Thank you, ma'am. I am ending my talk. Last slides. And thanks for your patience and also for your support.
Thank you very much.
I think if anybody has any doubt about these techniques, then I am very happy to answer it.
Okay. Now I would ask the participants if they have any queries related to this lecture. Please raise your hand. I will unmute you. Any questions from the participant side? Or you can also write in the chat box your questions.
Yeah. Yeah, there is a question in chat box. I also can read. Mike, what is the B3LYP and why is it is most popular function in density functional theory? Okay. It is also, I have already told that B3LYP is a hybrid functional. Hybrid functional means it contains, it overcomes the limitation of LDA and GGA, which was not easily predicted or not accurately predicted by help of LDA and GGA, but B3LYP that gives the better result. And we can also see in last experimental data that our calculated optical properties are very much close to the experimental results. And it is also in the way of progress of developing. Thank you, ma'am.
Okay, thank you very much, sir. Now we are well aware of the computational nanotechnology, so that also the experimentalist now can use that knowledge from the computational values in their experiments to create better nanomaterials with better functionality and better performance.
Yes.
Thank you very much, sir, for your nice presentation once again.
Thank you, ma'am,
Now
for
we'll
supporting and for supporting
you are very much
for
welcome, sir.
presentations because of interruption here is arises. Thank you, ma'am.
So now we'll move forward for our next presentation by our last esteemed speaker, Dr. Ashutosh Singh, who is an assistant professor of physics from Bihar University, Muzaffarpur. His title of the talk is Electromagnetic Metamaterials, New Possibilities for Future Applications. So Dr. Ashutosh Singh was previously the Dean of the Faculty of Physical Sciences at SRM University. Presently, he is working as an assistant professor at MP Senior Science College under Bihar University. Apart from his academic duties, he is discharging the duties as Development Officer of Bihar University, Muzaffarpur. He has authored or co-authored over 30 research papers in many reputed international national journal and conference proceedings. He is also reviewers of many international and national journals. He is supervising several PhD students in his area of expertise. The area of his current research and publication include modeling and simulation of microwave vacuum electronic devices and their subassemblies, cyclotron resonance measure devices, including gyrotrons and gyro TWTs and their performance improvements, etc. So thank you, sir, for being a part of our webinar. So I would request our participant to wait for a while until Ashutosh sir started sharing his screen.
Hello. Hello.
Yes, sir, you are audible
Hello.
now.
Okay, thank you, madam. Sorry for the interruption. Sometimes there are internet connectivity failure, but now it is connected. Okay. First of all, let me thank you to the patron of this webinar, Professor Dr. Nalin Vilochan, sir, who is fortunately the principal of our college also, and Dr. Mahila Mukhopadhyay, who has given the opportunity me for presenting my work in this webinar. Okay, let me tell you that I'm not going to present any mathematical kind of thing or any big research in this area. Just I wanted to present here the beauty of this materials research. Here I'm going to present electromagnetic metamaterials, new possibilities for future applications. So this is the metamaterials, which is slightly different from the nanomaterials. Okay, so in the last 2 days, we have heard so many speakers about the nanomaterials and nanostructures and the beauty of this structures, and that has changed lots of things in this research area, material research area. So this is the one kind of the metamaterials, which is also a very beautiful structures, and unlikely the nanomaterials, we are not going to use them atomic property of the structures. We are just using the effective parameters of the structure. So let me start my presentation. And the topic of the aim of this presentation is to encourage to attract the young researchers and young students into the material research area. Okay, so these are the outlines one by one. So first of all, what is the metamaterials? So the field of metamaterials emerged from the linear electromagnetism 2 decades ago. Just I wanted to add that it is not a very old area. It is just started nearly around 2000 year, and just 20 years before it has been started, and now it has covered most of the aspect of the physics in solid state, electromagnetics, optical magnetics, and so many area. And now, what is the metamaterials? So this is the metamaterials, which comes from the Greek letters meta, and which is the beyond, and the Latin word materia, which is the material. So electromagnetic metamaterials is a metamaterial furnishing the tailored electromagnetic response which surpasses that and structures. Now, a metamaterial is a materials engineered to have a property that is not found in the naturally occurring materials. So metamaterials एक तरह का engineered materials है. It is not naturally, ऐसा नहीं कि it is naturally occurring है या फिर we are going to fabricate at the atomic level. Just we have to engineer it according to our application or our need. Why metamaterials are interesting? These materials are made from the assemblies of multiple elements fashioned from the composite materials such as the metals and dielectrics. So materials are usually arranged in the regular pattern at the scales that are smaller than the wavelength of the phenomena and the influence. Their accurate shape, size, geometry, size, orientation, and arrangement give them smart properties capable of manipulating electromagnetic waves by clocking, absorbing, enhancing, bending to achieve the benefits that go beyond what is possible with the conventional materials. Here, since I am from the microwave field, so most of the things that will be related to the electromagnetic wave kind of thing, but it can be ranged, it can be scaled from microwave to optical to terahertz and optical lens also. So that can be scalable. Classification of materials. So based on the classification, 4 types of materials are here. First one, that is the ENG. Second is MNG. So now you can see, sorry. What are these ENG, DPS, and MNG? ENG is the nothing but this is the epsilon negative, and here it is zoomed out, that is the MNG, which is the mu negative structures. So now you can see these are the rings, which is the rings resonators. Second one, these are the cylindrical rods, which are the epsilon negative structures, and after that, this ENG structures and this MNG structures, both combinedly gives the DNG structures. And one of the beautiful application of this DNG structure is cloth. DNG for the double negative, where the epsilon and mu both are negative. So historically, just I wanted to tell when it has been started. In 1964, the Veselago had given a publication, and he told that there can be a possibility of simultaneous negative value of epsilon and mu. And after the 30 years of this prediction, Dr. D.R. Smith in 2000 century, he has shown the first time that the negative permittivity and permeability can be possible. And J.B. Penry in the same year, he has given the major breakthrough by utilizing this negative epsilon and mu by making a perfect lens. And mu is negative at 725 nanometer, at which it was given by in the same year till 2007. Now, just a little, we wanted to electromagnetic analysis. Any materials can be approximately
I request our participants to wait a while. There is again some internet connection problem from the speaker side.
Hello, am I audible, ma'am?
Yes, you're audible, sir.
Okay, sorry for interruption. Internet is creating such sometimes this problem. Okay, so now just we are discussing about these split ring resonators and rods. and these are providing the mu negative and epsilon negative structures. So let me skip some thing. This is the one structures you can see that where this rod there is a periodic structures of different rows, and you can see the permittivity value for certain frequency range, that is the negative, and permeability for that spring ring resonator, which is on the right side. You can see that for the some frequency range it is a negative, and because of that combination of split ring resonators and the rod, you can see that both of this is negative. So refractive index, which is the multiplication of epsilon and mu, you can see the refractive index of the materials can also be negative. And this is the mathematical expression that how can we write the refractive index for the material is negative. You can see the epsilon and mu for negative, you can write exponential I pi, and if n is equal to multiplication of epsilon and mu, then it certainly it will give the n is equal to epsilon and mu. So Veselago had done this electromagnetic analysis for the first time, and he solved the electromagnetic equations and showed that for different kind of combination of epsilon and mu, whether the wave is propagating or not, and based on that he proposed that when the epsilon and mu both are the positive, we call it right-handed medium, and if both are negative, then we call it as a left-handed medium. So yeah, this one. So this is the famous Snell's law. We know that this Snell's law. So that if one ray is coming on the interface of the surface, so partially it can be reflected and partially it can be transmitted, and based on Snell's law, refractive index of medium and the angle of incidence and angle of reflection can be determined, and that is called the positive Snell's law. So here you can see where if the second medium is the negative index medium, then the Snell's law gets reversed. So the angle of refraction, which was in earlier in positive medium, it was in other direction, so it gets reversed in the other direction, and we can see that. So with these two pictures, we can see that how we can differentiate within right hand medium. So the lower one is the right hand medium, where the phase velocity and group velocity is shown. You can see that the phase of each phase of wave is propagating toward the right side, and also the group velocity is also propagating toward the right side. So what we can say that for right hand medium, phase velocity and group velocity both are in same direction. But if you see the above pictures, then you can see the wave is propagating towards the right side, but its group velocity, its envelopes, it's moving in the opposite direction. So what we can say, the group velocity is opposite in the left-handed medium with the phase velocity, but for the right-handed medium, both are in the same velocity. Okay. This is the first structure reported in 2000 and was published in the Physics Review later. And this was the first practical left-handed or materials. And we can see that the transmitted power for the epsilon negative and negative, you can see in this picture. There's one of the pictures also. You can see here is an antenna which is radiating the microwave, and it is coming. So there are three medium: positive index medium, positive. Three medium are positive index with different Okay. Okay. So I think I'm audible now.
Yes, sir.
This can be realized with these pictures, how this negative index medium behaves. Okay, one of the structure, that is the PBG structure, that is called photonic band gap structures. That is also a periodic structure which give rise to stop band and pass band, one dimensional, two dimensional, three dimensional. And you can see in this picture, if there is a stop band, then the electromagnetic wave cannot propagate through the structures. And if we are considering any a passband region, then the electromagnetic wave can propagate through this structure without any attenuation. We can guide our electromagnetic wave from one place to another place. We can bend it, and we can make a cavity for confinement of the electromagnetic wave in some structures for originating. Now, finally, we are coming to the application of these structures. So many applications are there: super lens for hyperthermia treatment of the cancer, cloaking devices, absorbers, antennas, radar cross-section reduction, seismic protection, and sound filtering, etc. So, by using the metamaterials, we can create the perfect lens, and this perfect lens, which acts in beyond the beyond the diffraction limit, and we can predict that exact image of the structures, because if suppose convex lens is converging for some rays, so it will be act as a negative kind of thing, so it will be diverging kind of thing, and vice versa. So by using the four left-handed materials, we can radiate the microwave source for hyperthermia treatment of the cancer, so that we can give the desired amount of energy to the affected tissue for the treatment of the cancer. So this is the one of the beautiful application. And second one is, that is the cloaking. We can hide our device by using the metamaterials structures. So if you can see this picture, a object is inside a cloaking device, and if the electromagnetic wave goes inside this, then the it parts gets bends, and then again it restored after this structure. So we cannot able to see whether what is hide in this cloaking device. And this is the one of the beautiful pic we have taken from the internet. So by creating a variable metamaterials, we can hide even the human also. So this can be possible, but what I think that there is possibility of bandwidth limitations, polarization effects. So there are so many things which we are struggling nowadays. If we are able to get a wide band, then certainly we can make a invisible man also. Even we can see that if you are looking towards in front, then but you can look your back side also. So or you can hide yourself also in these two pictures you can see. And what little I have worked in my research, that is the absorber kind of application. So we have done so many structures for absorber kind of application, and this metamaterial absorbers gives so many applications for improving the radiation pattern of the antenna, for suppressing its side lobes. Terahertz metamaterials perfect absorber as the frequency selective thermal detectors and spectrum modifiers. Metamaterial absorbers based tunable microbolometer. Terahertz waveguide circuit application for millimeter transmitter lines, microwave phase shifters and filter, and so many. This is the some applications of the absorber which I am working on. That this is the structures which I have worked, and it was this one structure I wanted to show, that you can see there are three split ring resonators. One is in microwave region, another is invisible region, and other one is the infrared region. So by just scaling the structures, the structure is the same. By scaling the dimension, we can create, we can make it operational in different frequency regime. These are some structures. So these structures can give a wide band response. You can see these are split ring resonators. By some, I have taken some results from published literatures, and we have more than 10 gigahertz bandwidth. So it's quite high. This work I have published, and 4 cells we have used in a 1 unit cell. So that will give a good response and a wide band response. So now coming to the out of these structures, I just wanted to show some more structures. Let me skip all this. Yeah. So what I am doing, that is for antenna purpose. So that gives an improvement in the bandwidth and performance of the device. Okay. So yeah, radar cross section. So metamaterials can also be used for radar. We just wanted to suppose our warships in the air. So we just wanted to hide our warships from the reach of the radar of the enemy. So just we can coat over the surface of the aircraft with the metamaterials, and we can reduce the radar cross section, and we can hide our spacecraft in the reach of the enemy's radar. In the seismic production, metamaterials can also be utilized for the seismic production for manipulating the acoustic waves produced in the seismic. So yeah, sound filtering. In sound filtering, it can be also used. An acoustic material designed for control direct and manipulate sound waves. Like electromagnetic waves, sound waves can also be manipulated using these metamaterials. Now, just few slides more. So this is the one of the structures, latest structure you can see in the image, where the split ring resonator is attached with 2 vector diode, and by eliminating the light on this vector diode, which is light emitting diode. So this is the we can control the frequency, operating frequency of the device. So this is called the tunability of the metamaterials by externally external optical source. These are few structures which we have taken from the internet. So these are the 3-dimensional optical metamaterials. You can see the beauty of these structures, and this gives the very promising result in 3D metamaterials. You can just visualize, and these are all of the optical metamaterials. Now coming to the optical, these are some structures for the optical metamaterials. One simple application of terahertz metamaterials in terahertz application also for detecting the fungi and bacteria of the things. You can see in the left hand side, electromagnetic wave is transmitting to the structures where the bacteria are on the surface, and there is a metamaterial structure. So metamaterial structures with fungi and without fungi, you can see there is a frequency response in the below. With fungi and without fungi, there is a phase shift in the frequency, and with this phase shift, we can determine the exact location and position of the fungi and bacteria, and its number also. So now finally I am concluding my talk. So metamaterial structures are able to mitigate the hurdles in material research. Whatever the hurdles we feel in today's material research, we can mitigate by using metamaterial structures. So it will be suitable to integrate a device ranging from the microwaves to terahertz waves and beyond that. So one of the major challenges is to build the 3D nonlinear metamaterials for the better performance of the device. Now, these structures have the diverse applications in optical filters, medical fields, remote sensing, aerospace, sensor detection, infrastructures monitoring, smart. I have just covered few of the things. There are so many applications which I could not cover in this presentation, but you will find so many applications in the and of course, the invisibility can also be possible with the metamaterials. So now, thank you for listening me. And question, just I will be very happy to answer you.
Okay, thank you, sir. Thank you very much for such a nice presentation and so much informative presentation. We came to know much about metamaterials and its application. Now I would request questions from participant. I think there is question from Dr. B.C. Rai sir. So I would request Dr. B.C. Rai sir to unmute yourself and ask the question.
Thank you, sir, for very informative lecture. Am I being heard? Hello.
Yes, sir, you are
Hi,
audible.
yes, sir. Please ask your question, sir.
I just have a query.
Sir,
What is difference between metamaterial and topological materials? If you have
metamaterials
some
and
topological materials.
just what I think, sir, metamaterials can be engineered with some properties like epsilon and mu, and we can just create by using any materials for our purpose also, and by taking it in the periodic manner or some non-linear fashion. But in other field, but we are using the beauty of a structure. Suppose we are using the nanomaterials. So nanomaterials are with what we do. What we do, we fabricate the materials at the level of nanoscale. So that is a different thing. Here we are not going to fabricate. We are just using a specific
I think
Hello.
Dr. Asutosh sir's battery was low and his PC is off now. So I think
Okay, it
Dr.
was
Rai,
nice lecture.
it is a nice lecture, and we are thankful to Dr. Asutosh Singh, and also thank you, sir, for your question. So with this lecture, now we will conclude our second day of webinar, and formally now I will ask Dr. Lalit Prabha ma'am, Assistant Professor, Department of English, for vote of thanks.
Warm greetings to all. I'm Dr. Lalit Prabha, Assistant Professor, Department of English, MSKB College. I'm here to formally present the vote of thanks, and I take this opportunity to thank our Honorable Principal, Dr. Nalin Bilotan sir, for guiding us and motivating us to conduct webinars in all subjects. His readiness to sort out even the smallest of issues is highly laudable, and I thank you, sir, once again. Now, I would like to thank all the speakers for their valuable contributions towards making this two-day webinar a success. First of all, our first speaker, Dr. B.C. Rai, who is an Associate Professor of Physics in Patliputra University, Patna, and he spoke upon the topic quantum dots and solar cells. Thank you, sir, for such an enlightening lecture. We're very glad to have you here and hope to have many more sessions with you in the future. Next, in his presentation was Dr. Tapas Pranmamani, Assistant Professor of Physics from NIT Andhra Pradesh, and his topic was Nanostructures for Drug Delivery Applications. We thank you, sir, for your enlightening lectures and giving us such a valuable chance to know your views. We had with us also Dr. Nipur Biswas, Research Associate, CSIR, Indian Institute of Chemical Biology, Kolkata, who shared her views on nanotechnology, precision medicine, and cancer. Ma'am, you gave a very enlightening lecture, and I'm sure we came to know very new aspects from your valuable presentation. My heartfelt thanks to you, ma'am. Our fourth speaker was Mr. Rahul Kumar, Assistant Professor of Zoology, Magad University, Bodh Gaya, and his lecture was on an efficient nano formulation for ophthalmic application. Sir, your deliverance really gave us a good view on ophthalmic applications, and it was something new for us to learn. Thank you very much, sir, for such a good lecture. In the second day of the webinar, we had with us for the first speaker, Dr. Navneeta Kumari, Assistant Professor of Physics, BRA Bihar University, on nanomaterials, broad spectrum for device application. Ma'am, your presentation was really very good, and I'm sure all participants must have benefited from it, and we're looking forward to such enlightening lectures in the future also. My heartfelt thanks to you, ma'am. As the second speaker we had with us, Dr. Ayan Mukherjee, Assistant Professor, Patliputra University, Patna, with his topic, Future Nanomaterial-Based Energy Storage Systems. Thank you so much, sir, for such an engaging lecture, for the contagious fervor with which you presented your lecture. We are thankful, sir, for you to have been here with us on this webinar and for making this a very special day. Thank you, sir, so much. As the third speaker, we had with us Dr. Manisha Bajpayee, Assistant Professor, Bihar University. Her topic was Application of Columnar Mesophasic Structures in Photovoltaics. Thank you, ma'am, for your very, very intelligible presentation. We were all enlightened to have you here. Thanks to you, ma'am. Our fourth presenter was Dr. Dheeraj Kumar Pandey, Assistant Professor from Ellen Mithila University, Darbhanga, and he gave his lecture on computational study of nanomaterials. Thank you so much, sir, for having been here with us in this webinar on the second day and giving your very powerful lecture and making this a special one indeed. Thank you once again, sir. And our last speaker was Dr. Ashutosh Singh, Assistant Professor, Bihar University, Muzaffarpur, and his deliverance was on electromagnetic metamaterials, new possibilities for future applications. Indeed, sir, in spite of a few glitches, technical glitches that was not in anyone's hands, you tried to make the best use of this time and gave a really befitting lecture. Thank you from my side once again. A very special thanks to all speakers and participants indeed, without whose presence here, this webinar would not have been possible. So I once again take this opportunity to thank all participants, viewers, and of course, my colleagues present here with me in making this webinar a success. I'm sure we all have gained a lot from the lectures of our enlightened speakers. We hope to conduct many such enlightening webinars from other departments too in the future. Thank you all once again for your cooperation and patience. In spite of some technical glitches, the webinar has achieved its aim. I'm very sure about it. So now we formally end this webinar. Thanks a lot to one and all. Have a good day. Thank you.
So now we are ending the webinar. Thank you.